Thank you for the introduction. Yes. Hi, everyone. My name is Emma Johanna Puranen. I'm very excited to be presenting here at BayesiaLab. I am a PhD student at the University of St. Andrews, and I do interdisciplinary research that bridges astronomy, media studies, and data science. So today I'll be talking to you about mapping changes in science fiction world building in response to scientific discovery. And of course, I will be using Bayesian networks to do so. So to provide a bit of justification and my research question for why I'm interested in studying this in the first place, I'm very interested in science communication, and I'm interested specifically in science fiction as a tool for science communication and science literacy. Science fiction is, of course, a genre of fiction, but it is always based in or has some inspiration from scientific fact. So a lot of people who read science fiction are encountering ideas from science in the science fiction. So how is this happening? What discussions are scientists and science fiction creators having? Well, it's this sort of back and forth, as you can see in this little diagram I've got on the side. There's conversations happening in both directions. And I'm interested specifically in how scientific concepts are passing through the medium of science fiction creators to the general public. I'm investigating this with exoplanet science specifically, which I will go into detail on later, because exoplanet science has recently undergone a big change. So I want to see if that is reflected in the way it's portrayed in science fiction. It seems like the perfect sort of tangled interaction to try and tease out with a Bayesian network. So the focus question is, to what extent are scientific concepts about exoplanets diffused through science fiction? And to do this, I take a big data digital humanities approach. So some background on the scientific study of literature. Most studies of literature are close reading, are case studies. You can write entire papers on single chapters of works of literature, but that's the opposite of what I'm doing. I'm following this methodology that comes from the formalist school of thought. The formalists were a Russian school of literature theorists that started in the 1920s. And they're so called not because they're fancy, but because they focus on the form of literature. So this can look like things like taking bird's eye views of genres. So this graph is an example from this book by Franco Moretti in 2005, where he's graphed the market share of various genres over time. And here you can see the rise and fall of different genres. And that is a piece of information that you would never get if you were, say, just studying one specific Gothic novel like Frankenstein from 1816, for example. So in losing some detail, you're gaining the bigger picture. This is another example. These are not Bayesian networks, but they're a little closer to Bayesian networks. What these scholars have done, and this is more of a natural language processing problem, is they've made social networks of character interactions from various novels. So this is how often two characters' names are in proximity to each other, or two characters are conversing with each other in a novel. And you can see just from looking at these images, the wider social structure of each of these novels. You can see, for example, that Pride and Prejudice is very focused on its main character, Elizabeth Bennet, whereas Vanity Fair has this much wider network with multiple main characters and lots of side characters. So these sort of digital humanities techniques allow us to see literature in a different way and do allow for the scientific study of something that a lot of people, I think, are unaware that you can study in this way. And I'm very excited by this. And I have decided to study science fiction, the overall genre, with Bayesian networks. So the bird's eye view of my methodology is I've collected data on fictional exoplanets in science fiction. Again, I will explain exoplanets in just a minute. I've created a Bayesian network using structure learning, using machine learning to find the network from the data. I've used Banjo from Hartemink from Duke University to do the structure learning. I've investigated the resulting networks using BayesPiles to help with decision-making for the best methodology, and I've visualized with GraphViz. So why exoplanets? What are exoplanets? Exoplanets, that's just the jargon term for planets outside our solar system. So those are a very common setting in science fiction stories from both before and after the discovery of real exoplanets. I said earlier, there's been a big change in the field. That big change has been the very discovery of real exoplanets. We didn't know for sure that they existed not too long ago. Exoplanets are also mostly not taught in school. People are mostly familiar with them through science fiction. Try to think right now if you've heard of any real exoplanets. Can you name any? Or are you mostly familiar with fictional ones? And before I switch the slide, I also want everyone to think, you might know this already, but think, what year do you think we found observational evidence of the first planet outside our solar system? If you have a year in mind, I'm going to change the slide. The answer is 1995. It may or may not be the case for you, but for most people I talk about this with, that's much more recent than they thought. A lot of people think that we've known for sure that exoplanets exist for much longer, but they're a relatively recent discovery. However, for me, this is a very good opportunity because we have decades and decades of science fiction works from before 1995 as well as from after. So I have plenty of data from both before and after this big scientific change. There's been this whirlwind of discovery since 1995. We found over 5,000 exoplanets to date. And the reason that it took so long to find them is that they're so dim. They don't give off light. They're very dim compared to the stars they orbit. So usually we can't directly photograph them. Most detection methods for exoplanets are indirect, based on observing changes in the host star. For example, one of them is the transit method. You can see it's the yellow circles on this exoplanet census diagram. The transit method is based on an opportune alignment of the alien solar system with our line of sight from Earth, where you can see the star passing in front of the planet passing between us and its star. So it's blocking some light from the star. If you're taking pictures of the star over time, you'll notice a periodic dip in the brightness that can tell you there's a planet and how long the planet's year is. You can see on this chart here, the exoplanet census. We've got orbital period, that's the length of the year, on the x-axis, and planetary mass on the y-axis. And you can see that a lot of these planets have short years and are much more massive than the Earth. So this is a very different population of planets than we're familiar with in our own solar system. Right from the first discovery, we were finding classes of planets that don't even exist in our solar system. And I apologize for these names. Astronomers are not good at naming things. But the very first discovery was what's called a hot Jupiter, which is exactly what it says on the tin. That's a gas giant planet that orbits very close to the star. In our solar system, all the gas giants are very far from our sun, but we found a lot of these planets that fit this bill of being gaseous and very close to their star, as well as what are called super Earths, which sort of fill another gap in our solar system. They are intermediary in mass between Earth and Neptune. So we found entirely new classes of planets that have made people go back to the drawing board on theories of how solar systems form exactly. But the overall picture I want you to take away from all of this is the fact that a lot of the exoplanets we've discovered are very far from Earth-like. And some of that is due to the difficulty of detection and biases in our current detection methods, which you can clearly see from this graph, from the separation of the blue and the yellow, for example. But a lot of that is just our solar system is not necessarily the norm cosmically. There's a lot more types of planets out there. Sort of just for fun, I will stress that this is a work in progress, but I made a Bayesian network from just over 2,000 of the discovered exoplanets that we found. And this sort of further illustrates what I was saying about the real discovered exoplanet population on the previous slide. Some of these links are trivial. They're physical and known. For example, orbital period is, of course, going to influence semi-major axis. Semi-major axis is how far the planet is from the star. And some of them are due to detection method bias. For example, as I showed on the previous slide, the discovery method will influence the orbital period. Those transit ones were closer in. And then some of these links do match real discoveries we've made about the population of exoplanets. For example, more massive stars seem to have larger planets, and that's something that we're figuring out why. And that link does show up on here. So that's just an overview of this discovered exoplanet population. Why do I care about looking at science fiction exoplanets? I mentioned we now have found over 5,000 real exoplanets, and that is new as of this year. So earlier this year, the New York Times ran this headline, "Imagine another world, now imagine 5,000 more." And I really want to focus in on the fact that they're using this word imagine. Although we have found 5,000 of these worlds, a lot of them remain data points that we know a couple of facts about, but we don't really have pictures of them as full worlds. The place where people are imagining planets in other solar systems as full worlds is and has been science fiction. So I just think it's interesting that they're drawing this comparison. Once again, there's this sort of back and forth between scientists and science fiction authors. Think of every time you've seen people talking about science fiction predicting things, which I don't think it really does. I just think there's a lot of back and forth between scientists and science fiction creators. So you get similar ideas. Here's a couple illustrations of fictional exoplanets. The reason I think scientists should care about this is because, as I said, science fiction is most people's exposure to exoplanets, to the point where you will see news sites reporting on actual exoplanet science discoveries and will be making constant comparisons to science fiction as a sort of shared cultural touchstone, like a point of reference that we all have in common. So every time they find a star in a planet in a binary star system orbiting two or more suns, they'll call it a Tatooine-like exoplanet. Or when they find one that's probably covered in a global ocean, they'll reference Waterworld. Or this text in black at the bottom is a scientist talking about what we know of this world that's been discovered, and then what we don't know, and finishing by saying lots of sci-fi stories to be imagined. So I think, like it or not, scientists should be aware of how science fiction is portraying their work, because a lot of the public is paying a lot of attention to that, and that is how they are influenced by this work. All right. All that said, what's my actual data? I've got this database of fictional exoplanets. I've got 155 of them currently in there. I have crowdsourced this through a Google form so people can submit planets that they want me to add. I will fact check all their data. It's an anonymous form. And that way, it's not only the works that I have consumed myself. I have 155 data points, and then I have these 9 variables, which I will explain by classifying the planet Tatooine, Luke Skywalker's homeworld from Star Wars. There's the arrow. So these first 3 columns are just metadata. The planet's called Tatooine from Star Wars. It first appeared in fiction in 1977. Then we get into our first variable, which is after discovery. Did the planet first appear in science fiction before or after the discovery of real exoplanets, which again was in 1995? This is from before, so I've classified that as 0. Is the planet in its star's habitable zone, the zone where liquid water could be stable on the surface, where life could exist? This is, so it's a yes. Is the planet orbiting a real star? That is it, say, fictionally in the Tau Ceti system, or is it in a galaxy far away, like Star Wars? So 0 for that. Is there native life on this planet? Yes or no? There is native life on Tatooine, so it gets a 1 for that. Is there native intelligent life on Tatooine? Yes or no? So in the Star Wars universe, humans are native to Coruscant. So humans are actually not the native intelligent life on Tatooine, but there are Jawas and Tusken Raiders who are native intelligent life on Tatooine. So it gets a 1. Can human characters breathe the planet's atmosphere? Yes or no? It's a yes for Tatooine. And then my only variable that isn't binary is what medium does the work come from? What's the media type? So this one's from a film. I've also got books, video games, TV shows, and podcasts, because science fiction is not just something that people read. It's increasingly something people watch or play in the form of a video game. Then I've got is gas. So that's really the planet type. Is it terrestrial or gaseous? So this one's terrestrial. And then the last one is established non-native humans. When I was going through the life and intelligent classifications, I kept coming across cases where there would be fictional exoplanets that had established populations of humans that had been there for hundreds or thousands of years, but were not native to the planet. It was happening so often that I gave it its own column. So that is true of Tatooine. So I went and did that for every planet in this database. The data collection was really the bulk of the work here. And because I was talking about the population of real exoplanets earlier, I wanted to do a little bit of population statistics for my fictional exoplanets in the database. So here you can see I did intentionally select about 50-50 from before and after the discovery of real exoplanets. But the rest of it is fascinating because the stuff I was showing you earlier about real exoplanets, remember, a lot of those were very big and very close to their star. A lot of these have Earth-like features. More than half of them are in the habitable zone. More than half of them are host to life. More than half of them are places where human characters could breathe. None of that is particularly realistic scientifically, but it makes sense given that science fiction is written by humans, for humans, typically about humans, for the necessity of the plot. So these are 2 populations that I don't really think it's fair to compare them to each other, but I just want to highlight that in science fiction, you're going to find a lot of more Earth-like worlds. I've also got the media type breakdown here. You can see it's mostly books, but I do have some representation from all these other groups. So without further ado, here's my current Bayesian Network visualized with GraphViz, and the influence scores were calculated in Banjo. So the influence scores between variables are color-coded. They are positive if they're blue and negative if they're red. And then the black one is non-monotonic, which I will explain in a second. Then the influence scores are written next to the links. And these range from -1 for the strongest possible negative influence to +1 for the strongest possible positive influence. So there's a lot of things that would be expected here. There's positive influences between things like life, humans breathe, habitable zone, intelligent. Specifically, life to intelligent. We can't have intelligent native life without having native life. So that gives something to compare these other numbers to. I'm very interested in the fact that real star appears to be isolated. I had been thinking that might be a proxy for how much science the author is paying attention to. Maybe it would be negatively linked to humans breathe, but it seems to be isolated thus far. I find most interesting anyway, the results from after discovery, which again is the one of, is it from before or after the discovery of real exoplanets? So we've got two negative connections. Established non-native humans negatively influences after discovery. That means after, in works since 1995, it's less likely you'll find established populations of non-native humans, and it's also less likely you'll find planets with intelligent native life. I think this is fascinating given a bunch of the discoveries from exoplanet science of a lot of these very strange, very unearth-like worlds that would not be very friendly for human habitation, for example. So I think this might actually be a bit of a case of truth being stranger than fiction and fiction catching up a little bit. So as for my conclusions, I'm mostly very excited that this methodology can be used to study literature. It can reveal these trends in the genre of science fiction, tell us how writers world build their planets and how scientific discoveries influence fictional planets. And these results thus far show that fictional exoplanets have become less Earth-like since the discovery of real exoplanets, even though my database is still dominated by Earth-like worlds. Because of what I was saying, again, it's often just necessary for the plot. This does mirror real-life discoveries, which have received media coverage. A lot of you might have seen, for example, popular science articles saying world where it rains diamonds or world with magma oceans and stuff like that. And I think a lot of science fiction writers are picking up on that and including that in their work. So for my future work, I'm going to be adding a lot more fictional exoplanets to the database. I want to make it more representative of what's out there, especially since it's currently very dominated by Western English language fiction. I'm working with one of my advisors is having some of her undergrads who are multilingual do translation projects, and hopefully I can add some planets from that. I have also thus far been a bit hampered by uncertainties in data. Thus far, I've only included data points for which I can answer all of my questions, but there are some that I haven't included because I'm missing one of them. And a lot of common techniques for working with uncertainties in data and Bayesian networks involve like averaging the rest of the column or figuring out what makes sense based on what else is true for that data point. And it just doesn't make sense for mine. And then also as my database grows, the network will grow in complexity and I will have to keep making sure I'm using the correct methodology. Yeah, and I'm a member of the St. Andrews Center for Exoplanet Science. We do a lot of work, not just on discovering exoplanets and characterizing what they may be like, but also in thinking about things like space ethics and humanity's future and space law. And what would it be like if we got a message from intelligent aliens tomorrow and all sorts of wonderful interdisciplinary problems like that. You can find our website there and you can find me on Twitter. And that is my presentation. I will happily take any questions.